Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, hello everyone, thanks for coming. Today I'm happy to introduce Professor Shawki Abdallah from the University of New Mexico. Professor Abdallah is the chair of the ECE department there and has a background in control systems, and today he'll be talking to us about control theory and applying them to the computing systems that we work on here. Professor Abdallah.
Okay, thank you. Thank you very much. Thank you for coming. I didn't expect that many people, 96, wow, that's a lot. Anyway, as Ripal made the introduction, I'm with the University of New Mexico. I'm a professor there. I work in control systems, but I'm also the chair, so I have to tell you a couple of things about my department in particular. Especially today's weather, reminded me of the weather in New Mexico. So I just wanted to show you this is the nice building, the library at the university, and that's what it looks like about 300 and I don't know how many days, right, Henry? A lot of days it looks like this. Anyway, we're a fairly large university, about 32,000 students. We get a lot of funding from mostly from federal governments. In total R&D, we ranked about 85 out of the almost 600 universities and colleges, and we're a research extensive one. My department is we're 32 faculty. We get about 11 to 12 million in contracts every year, and this past year was a really good one. We have new grants, about 18 millions, which is pretty decent for a university or for a department our size. What's best about it, though, is as you will see, we're much bigger at the graduate level. In fact, we get about 4+ PhD students per faculty. Graduate about 18 PhDs, and this is what I was talking about in here is we have about 121 PhD students or candidates and about 100, so to about 230. It fluctuates between 230 to about 270 graduate students. We're a lot smaller at the undergraduate level. Anyway, that's all I'm going to say. I have to say this, this part about the university. Now we can get on with the talk. Let me start with some disclaimers. It's too easy these days to take something from someone and put it in your, if it makes the point rather than start it over. So I'm going to give credit, and unless I claim it, then it's somebody else's. That's how I'm going to do it. I'll tell you which ones are mine. Otherwise, I took a bunch of stuff, and I have references to these people throughout. But, Professor Hellerstein, who used to be at IBM, he's now at Berkeley. A couple of other researchers and professors, I took the liberty of taking some of their slides. I'll tell you some of them when we get there, but I'll explain them and hopefully in my own words and give you the interpretations that I'm hoping this is what we're going to get across. And mostly this material is not original because while I didn't know what the audience is going to be like, I was told that there are not too many control theorists at Microsoft. And I believe it. So there are not that many control theorists anywhere, actually. So, probably not unusual. But I wanted to get across some really top-level points and then dive maybe into a couple of them. So I like to start with a punchline, kind of like the executive summary of the punchlines in here. The first thing is feedback works even if you don't know what you're doing. It works. So that's the first thing, is that if you're not sure of how to do something, how to control something, measure some output and feed it back and play some, and it works. Now the danger with that is that it could work too well or it could take you in the wrong direction. It changes the behavior of the system, sometimes in unpredictable ways. So the reason a lot of people do control without knowing that they're doing control is because it's very simple to say, as I'm doing right now, I'm looking at you, I'm trying to detect something from you. If I see people shaking their heads, I get the feedback that you people are understanding exactly everything I'm saying, so I'll speed up. If I see people going like this or, starting to read their email, I figure I'm losing something. I'm getting feedback from you. So feedback in everything we do is something that's like very basic. In fact, nature is very good at doing feedback. And it turns out that it works. But it could change the behavior of the system in too many or two different, in many different directions, and it could get you in trouble. One more thing I want to tell you is, unless you spend your time modeling the system, trying to understand it, you'll spend a lot of time trying to control it and trying to tweak it. So you're going to have to spend the time someplace. You either sit down and trying to understand what you're dealing with and spend a lot of time doing it, or when you get to the controls part, when you're trying to change the behavior of the system, you're going to spend a lot more time on that. So you have to spend it someplace. You decide. In some cases, it's much easier to do it at the front end when you know what the system is, or when you can write down some descriptive models for it. In other cases, you can't. Your system is too complex. You don't know what it is. It's a black box. You do some experiments, as we'll talk about. And then finally, there's no free lunch. If it's too good to be true, it's too good to be true. If someone tells you they're going to give you, this behavior with so many, without paying anything for it, it doesn't work. In fact, there's some fundamental limits that I'll touch upon when I talk about some of the feedback controllers that we deal with. And it doesn't matter what system you have. You can throw all kinds of resources. You're not going to violate the second law of thermodynamics. You're not going to violate Shannon's capacity and so on. They're fundamental things that you're not going to be able to do anything about. So if it's, again, too good to be true, it is too good to be true. So just go back and try to trade-offs. There's always trade-offs in this thing. So these are the punchlines at the high level. Now let's get into it. What I wanted to say is that starting from the beginning of times for control theory, control has been applied since the Egyptians and the Greeks and so on. You can go back to that history and you see people who were designing mechanical gadgets as well as trying to do some water type control for flood control and so on and so forth. Control theory, in the sense of what we have right now, what we understand as control theory, has a much more recent history, but it's really intertwined with computing theory and computer science. From the beginning of times, there was this idea that cybernetics and feedback are connected. You can go back a little bit earlier, but probably Norbert Wiener was one of the first people to look at feedback in the man and the machine, the way he described it. He looked at neural networks. He looked at trying to track aircraft, for kind of aircraft fire control, or trying to track airplanes to shoot them down. But he was also very interested in this idea that if you put feedback around the system, you can change the dynamics of the system in a fundamental way and make it do something totally different from what it was originally doing. They separated, a lot of companies such as Microsoft. You do a lot of computing. You work in computing, and everybody does control in one way or another, from car companies to airplane companies to Honeywell to people who do building automation and so on. But they separated. They really developed in different ways with the occasional intersection. For example, a lot of the controllers right now are implemented with microcomputer or with computers. So you need to understand at least at that level. But beyond that, there are a lot of interesting things that are happening now, basically because of the networking aspect of the world we live in. So a lot of problems in control theory are spilling over into some of the problems you guys are dealing with, and vice versa. You're getting to build data centers and large distributed systems where you need to control some resources, access to them. And while you've been doing that in different ways, I believe, or I'm hoping that I can convince you that control theory that was developing in a different direction has something to contribute to your problems. And that's hopefully the theme, or that's what you will walk away from with the talk. And the last thing I want to tell you in the abstract is that I'm hoping to show you that control theory is more than simple PID. How many people know what PID stands for? Everybody knows, right? Yeah. Proportional integral derivative. 99.9% of what's out there is this PID. And again, it works. I mean, you know, it's not bad. The point is, most of the problems you're interested in are not going to be solved with PID. PID has done its job to solve almost everything else, but you know, the problems that you guys are dealing with and most people are dealing with will need something beyond the simple proportional integral derivative, which I'll talk about. So I started with some of the historical links. I talked about Norbert Wiener. Tarski actually looked at the incompleteness of arithmetic, and some of the stuff he came up with, the quantifier elimination, turned out in the 80s and more recently in the 90s to have implication in control, to be able to solve some control problems by stating them as quantifier elimination problems, which Tarski was interested in and came up with algorithm to show that, you know, you can eliminate these quantifiers in a finite time. Of course, at the time, people didn't care about complexity. It turns out to be doubly exponential. So when people in control saw this the first time, they thought they solved, you know, the holy grail. You know, I can phrase a lot of problems as a quantifier elimination. Therefore, I can solve my problems. Well, and then the idea was the first time people in control came across it, they said, oh, look, computers are going to get better and better and faster. Therefore, I'm going to be able to solve all my problems. Of course, you know, we know from computational complexity that's not going to be the case. It doesn't matter how fast your computers are going to. If you have an algorithm that's doubly exponential, well, at best exponential, it's not going to work. You know, the Jacobson algorithm for doing the congestion control, at the time he motivated it from a controls point of view, but recently it turns out, and I'm going to talk a little bit about this, it turns out that this is actually can be described very nicely as a resource allocation problem and has a very nice underpinning control theory. It wasn't how he came up with it, but that's exactly what came up, what ended up happening. There is this feedback between control and computing, as I keep saying, is that, you know, you do congestion control, you do you know, access control in some cases, you do a lot of control without actually calling it that. At the same time, computers, because of computers, we are able to implement some new controls and so on. And then finally, the thing about where we are now is the control of networks and the network control, which is kind of what got me interested in this and how I got in touch, or how Ripal and I came across each other, is that we're trying to control networks, and we're also controlling across the networks, because we have systems right now all over, and we're trying to control them across either a shared network or a private network. So we may have resources we're trying to distribute across a network. We may have, NASA may have a rover that they're trying to move across their own private network somewhere else at a distance, or we may be trying to do experiments across the United States because we have resources limited, and we have a special experiment or a telescope in one place, and other people need to control it and move it. So we have this, again, this idea of getting between this feedback between the two. These are some of the highlights, I would say, of when people talk about control in computing. I'm mentioning some of the people here that I borrowed from, or I use some of their stuff. The network flow controller, Chris Hollett and Shrikant. Frank Kelly is actually the one who started putting this congestion control, these ideas of the internet as the mathematical modeling of the internet. He's an applied mathematician, statistician, who basically wrote down the optimization that can be solved, or that is being solved in a distributed fashion, using the congestion controllers that we use in TCP/IP and others. There is in the early 2001 and so on, Herrstein and a group at IBM started looking at control theory. They came up with this book, Feedback Control for Computing System, based on their stuff, which is, again, kind of reintroducing standard feedback or standard control techniques to computing systems. Some people at the University of Virginia did some other work on quality of service differentiation. And then my understanding is Tariq Abdel-Zahir was here visiting a group, and he did some work in there. Jonathan Lau at Caltech follows up on some of these network flow control Mascolo, another person who's probably more of a controls person than most of them. Well, Shrikant is too, and Hallett. And then there's a group at HP that you guys are very familiar with, the IBMers and so on, who are working on applying some of these to control systems. So having this baggage and background, what does a control theorist do? What is control theory? What is it exactly? What is it? When you're trying to do control, as opposed to being a mathematician or a physicist, what you're trying to do is you're trying to prescribe a behavior to a system. And the difference between that and, let's say, somebody who's doing signal processing or communications is a signal processing will take a signal and they will say, well, look, I know there's something buried in there. I'm going to move or I'm going to change. I'm going to massage that signal to get the image out of it or the information out of it. A controls person does not care about that signal in particular. What he or she will care about is how to take that signal and then modify the behavior of the system. The example I like to give my students is you're flying an airplane and it's measuring 5,000 feet when it should be 10,000 feet. Well, the signal processing will say, well, I'm just going to add 5,000. It's 10,000 feet. The control theorist will say, no. If it's at 5,000 feet, I need to do something about it to move it. So they will take this signal. They cannot go back and change the airplane. They cannot throw people off luggage off the plane to say, okay, now we can go for the same power at a higher elevation. That's not how they can do it. They're going to have to, without going inside the system, they're going to measure things from the output and then change the input in such a way that the behavior of that closed loop is exactly what you want. That's really the idea. So how do you do that? Well, what you do is you start by describing what the system is doing. You decide what you can measure and what you can change. And then your job will be to design that block in between what you measure, what you can sense, and what you can change, so that the closed loop does exactly what you want. Not unlike your cruise controller or unlike the temperature control in the room, where you set it at some temperature, and what it's doing is it's taking measurements, deciding, am I above the 71 degrees? What do you guys keep it at here? 68? What do you guys keep it? I don't know in Seattle or at Microsoft. But you want to keep it at some level. And then, you blow cold air, you blow hot air. Now, what this doesn't account for is the fact that there is not 96 people in this room, because it may be designed to hold 96 people. So if you don't have 96 people, maybe the model or maybe what you're doing is not exactly the right thing. If you have the door opening and closing all the time and you have air blowing and so on, these are disturbances. That's where it gets interesting. It gets interesting because the model is inaccurate. You have uncertainties, and it gets interesting because you have disturbances, which are signals you cannot control, you cannot change. You can blow hot or cold air, but if I keep this door open all the time and it's snowing outside, then I'm going to be basically putting things out and not being able to regulate it to what I want. Now, throughout the years, you've had these periods, and most of the people are still using what the classical control period came about. The PID came out from the beginning of control theory to about the 1960s, where things were developing, mainly for linear systems, mainly for time-invariant systems, mainly for single input, single output systems. And it works. So most of the time, even people where they learn. It's funny to call something modern control in the, it ended, or, it's in the 1980s, but, it's always interesting to read these books. 1945, it says modern electronics or something, So anyway, modern control is the 1980s. This is the state space period, basically, where people started learning or started coming up with ideas that said, look, I can't just measure this input-output, and I'll talk a little bit about this, because there are things happening internally to the system. The state of the system is unknown. So I need to recover some of that, and that became actually a very clean, nice theory that culminated in the Kalman filter. This is, Kalman would be one of the pioneers of this period. Then people decided in the 80s and later that, wait a minute, this modern control, went too mathematical. It doesn't have too many applications, although this is exactly what was used, on Apollo, for example, to get to the moon and back. They said, well, we're ignoring some of the uncertainties. These are too perfect, these models. So they started accounting for the uncertainties again, which was the original reason for feedback, as I'll mention in a couple minutes. And then finally, after that, not finally, it keeps evolving. We get to a period of the intelligent, what people call the intelligent control. And, right now, I don't know what period we're in. Maybe the not so intelligent control, because these guys here, when they said intelligent control, they said, don't worry about it. Neural network will take care of it. Just things like that, that are, intelligent from the from the artificial intelligence point of view, which became very controversial. The fuzzy control and so on. Not because it doesn't work in some cases, but because it's oversold. It's saying, okay, yeah, you can do everything. Don't worry about modeling. Don't worry about doing this. We'll take care of it. So anyway, so let's get to the step-by-step control. Here's what you do. You first model. However way you want to come up with a model. I don't care if you just start asking questions. You come up to someone, first time you meet them, how are you, what's your name, what do you do, where do you go to school, etc. You're getting a model. You're getting data. Or you can sit down on a piece of paper and come up with a model. Okay? Get the model. Do the design. Okay? Because the model is going to tell you what you can do. Once you have the model in some way, either mathematical equations, data that you collect, anything, that will give you the design. You test it. And that's what people skip a lot of time. Well, in school they skip it. Outside, that's why you jump immediately to testing, right? You don't do, not at Microsoft, of course, but other places. Yeah. So you test it on your system, if you can. Some of these systems, that's what Boeing does. They do the wind tunnel testing, but then they fly it. They have they fly this thing over and over under different circumstances, and then you repeat. It never goes like just from one to the end. I mean, it doesn't. So you go back here and you say, okay, it didn't work in here. Where did I go wrong? Well, I didn't account for this type of uncertainty in my model, or maybe my model is too detailed. I don't need this. You change the design, change the test, and you repeat. And the secret of all of this, is that you have feedback. So you can do very badly in the model. You do okay in the design. When you test it, because you're doing feedback, it does help you. Feedback helps you because when your feedback is almost like getting a real-time information all the time, and it's adjusting to things in your model that you did not account for. Now, if you're too far off, it doesn't work. But if you're close and you get lucky to choose the right feedback or the right structure of the feedback, it works okay. The problem is, okay is not good enough anymore. Even if you're, you could, in the 70s and the 80s, we can have cars that get 10 miles to the gallon or whatever it was, And that was good enough, and we didn't care about this and we didn't care about that. But when you're trying to squeeze the last bit of performance of something, as is happening in some of your systems now because either of power considerations or because of performance objectives that your customer is asking for, it's no longer enough to just say, okay, I'm going to slap a feedback, so you really need to get into it. And here's where we first get to encounter our block diagram, or what we look like. So usually we call it a plant. It comes from the old terminology of chemical systems and so on. It's a plant. It's a physical thing that you're trying to control. You have an input U and an output Y. Now, nobody is going to give them to you. You're going to have to decide. You're going to have to figure out. And that's part of the modeling, is to decide what is it that I can change? What can I change in here? Well, in this room, for example, I can change the amount of heat that's flowing into it. What can I measure? Well, in an engine, I may be able to measure the temperature. I may be able to measure the mixture of air, fuel, and so on and so forth. What is it that I can measure? Now, unless you have a very simple plant, you cannot measure everything you're interested in. You can't. So the state of the system, the state, the actual thing that you need in order to predict the future is not available to you, and it will never be available to you. And in some cases, you don't want to spend all of your time doing that. It doesn't pay, for example, to sit down and try to model a car down to the latest component in every controller and electronic part and mechanical part of the car. It doesn't. If you're interested in making the car move at certain speed and so on, maybe all you want to do is consider it a point mass. Just it's a mass, and has an acceleration, and see what you can do. Maybe that's the level of modeling you want. Regardless, you need to get this part. Now, you get something which is the transducer. Really, what you can measure in here comes out not clean. It's a sensor or a transducer. Then you usually have a reference in here, and this is where the feedback comes in, and it's usually a negative feedback. It doesn't always have to be. So it's a negative feedback. There's an error between this B and this reference. You get an error signal in here, and this is what you design, controller. In some cases, you also design this. Now, I'm using here the variable t to denote time. Things are time varying, and I'm also putting in this thing called disturbance in here, because these are the inputs that I cannot control. This is the thing that in this room, it's the fact that things are being open, the door is open and closed. Maybe I have a draft someplace where I'm not accounting for, and so on. In an airplane, this is the turbulence. Okay? In your computer, if you're trying to do access control, it may be the number of people who are trying to come in and to get access to which are, you can model them in some way, or you can have some trajectories, but you don't know a priori if you're going to have one person or 100 people. Well, you may know a range, but you don't know exactly how many people are going to be coming in. So this is the structure. The job of the control engineer is to design this controller, and sometimes this transducer, although in many cases this is given to you, or this is part of it. So in general, you have three goals. You can regulate. In this room, I want it 71 degrees, I'm regulating. You can track. In an airplane, I'm tracking a trajectory. I'm going up at some speed, then I'm leveling off at this, and then I'm going down. Okay? These are the standard goals. You have other things. You have other secondary goals. And then you have the question of optimizing. Because once you do that, you can do it in a very inefficient way, or you can do it efficiently. Optimize means, okay, if I want to launch something from here to, I don't know, Mars, I want to do it at a good time. I don't want to waste too much fuel, because if I put too much fuel, then I can't put instruments on it, and so on. So you want to optimize something. The energy consumption usually is a good one for some of the applications you guys are involved in. So you will have things like, okay, you want some quality of service. You want to guarantee to someone a certain throughput, certain performance, but you also want to optimize the cost of something or of your of the energy consumed. All right, so where do you start? Well, you start again with the model. So I want to go back and drill this, a little bit, and then jump to some of the applications. So as I mentioned before, usually it's a mathematical description. Usually. It may not be for you, because you cannot write down a physical law that says, if I do this, then here's what's going to happen to all of these variables. Remember that remember this in here. This and this input and this output. You may not be able to write down a mathematical description that says, okay, U is a force and the output is going to be a position and velocity. If I could do that, then all I'm left with is to really figure out what are the parameters inside this plant. In some cases, I can. In an airplane, I know a lot of how I can do this. In a computing application, I really know very little about, even if I have access to this, I know very little of what happens in between. Okay? So what do I do? Well, instead of this model, which is the mathematical one, I'm going to have to do some curve or some data-driven model. So let me step back and talk a little bit about some models, because people use the word linear and in a lot of applications. In the context of control, linear means one thing, and that is it obeys superposition. How many people heard that? Superposition? Okay, so well, okay, so superposition, all it means is that if you double the input, the output will double. If you add two inputs, the output will double. If it obeys that, it's linear. If it doesn't obey that, it's not linear or nonlinear. Everything is nonlinear. There's nothing that's linear, except in a small regime, because even the simplest thing will go nonlinear on you if you push it, across its regime of operation. I don't care what it is. Everything eventually is going to either saturate, burn, do something. So there is nothing really that's linear across from 0 to infinity, from 0 input to infinity input. There's nothing that you can do that, because what it would mean is really that you have an infinite frequency response and an infinite something that will take in any input. It doesn't do that. Your car, when you're driving, your steering input, you can go between some angles. You cannot go all the way 360 degrees. You can't do it. Okay? You cannot push it past a certain limit. That's it. It's going to saturate, it's going to burn, it's going to do something. But linear turns out to be a great approximation or a great thing in the regime where we're normally interested in. Deterministic versus stochastic, a model of deterministic system versus stochastic. Again, very interesting because deterministic models, you know, if you put some input in, you know what the output is going to be in a deterministic fashion. Stochastic, you're going to have to resort to stochastic variables, to random processes to try to do these models. Time invariant versus time varying. Things that are time invariant mean that today, if I apply some input to them, some output will come out. If I do it tomorrow, the same output will come out tomorrow. Same output if I apply the same input. And it will do so forever and ever. Well, now you know nothing is like that. Your car, when you drive it off the lot, is going to behave nicely. 10 years later, after you've had your kids and everybody, your friends driving it, it's not going to behave the same way. It doesn't matter. You know, it's not going to. But we consider linear and time invariant as one of those easy or easier systems to deal with. Continuous time versus discrete time. Now, this is an interesting one because in a lot of control theory that developed, continuous time was much more comfortable for us. You know, continuous time is nice. You know, we differential equations. You know, this is where computing went a different way. You know, discrete time, right? So you guys went a different approach. But then, you know, we can have systems that are discrete time. We can design them in continuous time, discretize them, put them in here, and so on. There's some peculiarities in here that are interesting. Most of the time, things that I develop here, I can take there. But there's some things that happen here that don't happen here and vice versa. For example, in continuous time, time is reversible. You can go back and forth. In discrete time, it can't do that. Sometimes you get to a point in discrete time and you cannot go back, for example, if you have discrete time systems. Okay, so here are the models approaches that I mentioned. The analytical one is the one we're probably going to ignore because we don't have too much in at least in your application domain that follows this. You're probably dealing more with experimental models or rule-based models. Or this is what I would call data-driven model. So what you do here is, remember what I told you? You know, you have to spend the time either at the beginning or at the end. You have to spend the time modeling or you have to spend the time controlling. Well, here, analytical is, you know, you have the physics. You know what it is. You're building the system, but you also know how it's taking place. So what you do here is you sit down, you write down your differential equations or your difference equations. You go and argue with the domain expert. You say, look, you know, this is not working out. Give me something else. He may, you know, tweak some of the parameters for you and so on. And then you get to a point where you end up with this equation, and this is the oracle telling you this is the real system. Okay? Oh, that's my phone. Don't worry about it. Okay. The experimental one is in the case of what Ripal has, which are these systems that he cannot sit down and write down what happens from input to output. Instead, what he does is he has access to some inputs. He can measure some outputs. He collects data. Then he tries to do a curve, or data-driven models. He puts some models in there. And then he will use things like least square and so on to try to curve fit some of these systems. And then he tries them, or he validates them against, a different regime of data. So the machine learning folks would usually work with us on some of these things where you have not static things but dynamical systems where you can take a certain input and then maybe able to collect data and then come up with a model that explains it. The rule-based is the one that says, rule-based would be the fuzzy logic type things. I would say, okay, if I push on the accelerator, the car will go faster. Okay, versus saying, if I push by this much, here's what I can translate in here, or here's what I get out, and so on. It's a broad behavioral system, and this one, the problem with this one, in my mind, is it's a good rough estimate that gives you some things, but then you have to tweak it for the performance and for the system you're dealing with. Let me just go. I'm not going to go through this one because it's really not one that you want to deal with. This is the one you want to deal with, the experimental modeling. So really here, the couple of things that I want to say is that you want to apply characteristic inputs to the system. And this is, for machine learning, of course, you know that what you learn is highly dependent, or you have to make the assumption that what you're operating in the regime where your system is going to be valid, or your classifier is going to be valid. So you want to apply characteristic inputs to the system. When you're flying your plane, or if you want to use the example of an airplane, you would not apply an input that the plane is always going to be flying sideways. You wouldn't do that. It's not going to be a characteristic. You will apply some inputs that the plane is going to see, or the system is going to see, and then you want to go across. Here's an example of something here that's interesting. It turns out that the best thing you can do if the system is stable is to apply white noise. Why white noise? Because it has all frequencies. It excites everything. You can see it. That's why you do in identification, in system ID, you would want to apply things that are across the frequency spectrum. Where in practice, you would not dare do that on a system that's a black box. You wouldn't do that because you don't know what's going to happen, what kind of frequencies you're going to excite. But that would be a sufficiently rich input that you would apply to the system to get things out. Now you collect the input-output data, you postulate the model. And this is very key here. You postulate a model. You postulate it. You have to start to say, OK, I have some idea what the model is. Is it going to be a linear system? Yeah, probably, because we have a lot of tools for that. Can I make it a second order? Well, let's start with the second order, see what it does. If it doesn't work as a second order, maybe I should go to third order. Maybe I missed it completely, and what I should do is really make it a nonlinear, but with no nonlinearities, neural networks type things, or basis function type things, and so on and so on. And that's how you would get yourself a model that is not physics-based. That doesn't have. It may be the actual system may be a first-order linear model, and your system, for the inputs you applied, may be a 10th-order nonlinear model that explains exactly what's happening in here. That's what you're going to end up with. So the point about this is it's very key to postulate a correct model that's as simple as possible, and then try to get the best fit. Use the optimization methods, as I mentioned, to try to identify parameters, if you will, and then modify, go back, repeat. Once you have this model, now you're in a more comfortable place because you have a model. Therefore, I have this model. Now I go to my friend who's a controls person, and I say, what's in your toolbox? And he'll say, oh, well, you have a second order model. Try this, try that. Once you have the model, the controller is really much more simpler, or much more easier to approach, to get to at that point, because you have the model. Now you can test things and test different scenarios on the model. How am I doing? You guys okay? Not seeing heads going like this or anything, so I guess I'm still doing. Okay, now I want to talk to you about the linear time invariant systems. Remember, the first block diagram I put up was just any inputs, any out. I didn't put anything on it. Well, when you get to the linear time invariant system, and this is for continuous time systems, then you can go into the Laplace domain or the frequency domain. If you want to go for the steady state, you just look at the frequency omega. And then you can replace things in here. That plant, you can replace it with a transfer function, which has all the information you need. That's why we like linear time invariant systems. We don't need to worry about all the inputs in the world. Once we have this, we just figure out all the dynamics. That's it. Now, that's not what happens in reality to any of the systems. But again, it turns out to be a very good way, or a first-order approximation that works rather well, even for systems like airplanes, or complicated systems. So everything here is in the S domain, and what happens in the S domain is you can do block diagram algebra. You can combine things. I don't know what. Oops. You can combine things. This is missing in here something, but this combined block. You can multiply these two together. In fact, you start now looking at important transfer functions, and you can say things about the system by looking at the transfer function. For example, I will know that my closed loop system is stable from this reference to this output, from R to Y, if the zeros of the polynomial that happens to be here, or the poles of the system, are in the left half plane, or in the discrete time they will be within the unit circle. I will know that. I don't have to test anything. This is correct. This is it. So what my job ends up being is figuring out what should the G1 of S be to place the poles or the zeros of this down here in the right, in the left half plane. That's the design, which then I go to, a software like MATLAB, and then I plug in what this is, I plug in what this is, I tell it what the reference, what I want to do, and then boom, it will spit out a controller for me that will satisfy this thing. I have to tell it if it's just a constant, a P controller, a proportional, it will do that. If I put a PI, it will do something. If I put a PID, if I do, I can design at this point very, I wouldn't say it's just a straight trajectory except for the P controller, but undergraduates can do that. They deal with it very easily, assuming this plant is not too complicated. If it's too complicated, I can do numerical things, but I can solve it. That's it. Now, this will be the end of the story if it were not for the fact that you can't get everything. Remember, if it's too good to be true, it's too good to be true. I can start from the beginning and I say, I know I can stabilize this system. And I can stabilize any system you give me by looking at the plant. By looking at this, I can stabilize it. I can look at what this G2 is. Normally, it's a ratio of two polynomials. I can look at it, and I determine there is no pole zero cancellation, no common roots in the numerator and denominator. I know I can solve the problem, and I can spit it out in very organized way. In fact, if I do it in the right way, MATLAB will give me the answer in two seconds. What's the problem? The problem is this may not be the real system. This is a model of the real system. So if I put my controller and I trust it, religiously trust it, I believe in this controller, put it on the real system, if I missed something in the model, it goes berserk. So that's the first step. The second step is this controller is going to be as complex, if I do it like this, as the model of the plant. So let's say I have a plant which has 100 dynamic parts to it. Well, this controller here will be 100 minus the number of the output, so let's say 99 if this is single. Well, I don't want to build a 99 order controller. This plant may be something really complicated. I want to use a second order controller. I don't have the money to do it. I don't have the time. I don't want to build a 99. Plus, the more parameters I put in here, the more things can go wrong. So I want to start with something potentially that's not as complicated. I may want to fix the structure. Well, as soon as I say that, as soon as I say I want to fix the structure, the problem is unsolvable. This is where quantifier elimination came in and said, oh, well, you can find an answer to this. But as soon as I said, don't give me the answer that the mathematics are telling you this is the answer, but give me the answer of this order, open problem. In fact, not just open, but provably undecidable. And this gets back to my link with the control theory, with the computation, with the computing, theory of computing and so on. So even in the simple case like this, which is a scalar system and linear time invariant, it's a mess. Let's set this aside for a second and show you that this is what people have been doing. So this is actually an access control. I think this is a Lotus Note server. This is probably, I don't know if this is Hellerstein work or one of the other people, but basically, taken from one of the available references online. What they're trying to do is basically design a controller to maintain the constant queue length regardless of how many people are trying to get in. So you can accept them or not accept them depending on what this is what you're trying to control, this queue length, where you have the reference value in here. You see that the structure is the same. The sensor is what I called before the H of S, the transducer. This is really the system, the plant, and this is the controller. Slight abuse of notation here with the arrows and so on. Okay, so what you do is you write down their transfer functions, and people have done that. Now you see the z variable here because it's in the discrete time now, so they wrote down, rather than differential equations, some difference equations. They pull them together. Now what you can do is find this g of z. You have these. You have equations for them. You either identified some of the parameters, or you have find the g of z. And here, you try different things, that the model will tell you. In fact, a lot of times you'll see this curve. And this curve basically is only exactly correct for second-order systems. Second-order systems are things that have two, basically, if you're looking at discrete time systems, the current value of the output depends on the previous two values of the output, the previous two values of the output. So you have a memory, but it's at size 2. Okay? So if it doesn't depend on anything, if it's just like the current value of the output is the same as the current value of the input, that's static. If you have one delay or one memory, so the current value of the output depends on the current input, but also potentially on my previous output. So that my queue length depends on what it was before, as well as on what I'm putting in right now, or two of them, meaning I remember two of them. That's what it will be a second order. So if you look at it, you usually see things like this, and this should be familiar a lot of times if you have if I ring something, if I go like this to this, and you hear the resonate. Well, you don't on this, but anyway. If you hit this on a metal or on something, you'll hear the resonance. And this is what you're hearing. This is what the vibration is going up. There's a peak, and then it settles down. And normally what you're trying to do is you're trying to make things go to this level here. You want to do it as fast as possible. You don't want it to oscillate too much. You don't want it to go high in here too much. And you want this to be as steep as possible. So those are kind of figures of merit. For example, you request something from your server. You don't want it to go back and forth too much. You want it to go there very quickly, and you want it to happen exactly. If you request this type of level of service, you want this level. You don't want it high, and you don't want it low. Okay? So, in particular, here's how you would do this. This is the proportional control. You take that E, that error, and you multiply by a constant. Or in the S domain and the Z domain, it will be just a constant like this. You can do an integral control, which basically is memorizing something, and this is what it looks like in here, in the S domain. In the Z domain, it will be Z to the -1. It's one delay. Take the E, delay it by 1, and add it. And then the differential control, which is a derivative in here, basically, this is what effectively it is. It's really predicting if you are trying to do something in discrete time. And if you put them together, you get the P, the I, and the D, or the PID. The proportional basically provides stability and handles uncertainty. So if you don't know anything, just take the output, multiply it, or subtract it from the reference input, and multiply it by something very small. Start out very small, and then slowly and slightly turn it up. You will see the behavior of the system change. Now, unless you're super unlucky, it'll probably get better for a while, and then it will get worse. Now, you could be super unlucky because you may be on the margin, or you may be putting in the wrong sign of the controller. And this is what most people do. That's what they do in these controllers at home. That's what most people do. This is feedback. This is the thing that I ask you a question. Based on your answer, I adjust. I yell, or I smile, or whatever. This is all I'm doing. Now, the second one is the integral action. The integral action, remember what I showed you in here where this thing is going to settle down? Well, if I want to settle down really close to this 1, I don't want it to settle down here at the 0.8 or higher than this, then I need to have an integral action usually. The integral action is memory. Basically, it remembers what it was, and it tries to adjust for it. Okay? And really, it's a low-frequency filter. So basically, it cuts out the high-frequency changes. That eliminates them. Problem is, if you put too much of it, this is actually the S itself is, because it looks like something over S. The S is the pole, which happens to be right on the j omega axis, and it could cause oscillations for you if it's too high. The derivative, which also is known as rate control, it's really effective in the transient part, and it's really a high-frequency filter. It actually starts out small, and then it goes high, so it amplifies things at the high frequency, which is bad if you have changes, if you have a lot of changes. In fact, if you have noise, you never want to use this, and you always have noise, so, right? Because this will basically, anytime you have the noise and you differentiate it, something is going fast, so the slope becomes the part of the input, and if the slope is high, then you get yourself in trouble. But this is why you would use a PID. You put it in here, and then you have exact ways to try to do it. Now, here's what they did. This is experimental from that access control example. So here's one where you have you see the blue, the black in here is the reference. This is what you want the queue length to be. And this is the actual based on Ki. They're putting an integral, in here, and I believe a proportional with no delays in here. And this is how much you can control the maximum number of users. So this would be what's considered good. Here's one that's bad, because it oscillates in here. See, you're letting people in, you're letting people out. You're saying from 0, okay, I can accommodate whatever, 150, I can accommodate no one, and so on and so forth. So this is one where the Ki got to be, well, it's the same, but the delay here is what's killing you. Same thing here. You have too high of a gain. Remember, I told you the integral term, you shouldn't have it too high. Boom, you get the oscillations and so on. So this is something where, this computer engineers, scientists, and so on, took a PID, modeled the system. This is the first step, really. So here are some of the examples that happen to appear a lot of places. These are a lot of, some of you are probably very aware of these. This is one that actually John Ghanem just walked in here. That was his master's thesis, where we were doing distributed load balancing, trying to control the load for a lot of computing nodes. And we had delays, which was the interesting twist in here, because a lot of the load balancing is done on one machine. This was supposed to be done across for an application that the FBI had for databases that were spread across the United States or the world. This is something that's catching a lot of attention these days, is where you have to try distributed control for sensor networks. Either you're trying to put the sensors, distribute them some places to be able to collect information, or other reasons why you would want to distribute the control. Okay, remember I told you the model. Well, what I should have told you is model the uncertainty as well as the model. So it's good enough to say, okay, look, I can nail this model, but most of the time, you don't want to nail the model. You don't want to say exactly what the model is, because it gets too complicated. Instead, what you probably want to do is look at a model that is nominal, that fits most of your cases, and then model the uncertainty, model the family of systems. And you get different ways to do this. There was a very interesting work in the 80s to deal with parametric uncertainties, i.e., I know what the system is, and we're talking linear systems for the time being, although this approach, parametric uncertainties can handle more than linear systems, but let's talk linear. So I know what the system is. I know that there is a numerator over a denominator of a certain order, but I don't know the values of the parameters in that system. Well, it turns out that this gentleman, who was a young researcher in the former Soviet Union, had solved this problem in an obscure mathematical journal that nobody knew about. 5-10 years later, it appeared that in some of the Western literature, and for about 10 years, people were doing this work, trying to analyze or trying to study systems that had parametric uncertainties. It turns out it's very efficient for analysis, but really difficult for design, exactly because of the problem I mentioned before, which is you have to fix the order of the compensator. You have to say it's a second order or a PID, and then it becomes extremely difficult to do design. Okay? The solution to that turns out to use randomized algorithm, which is what we've done for a long time, and it was very successful doing that, to get around the computational complexity. It's really the old adage. If you're faced with a problem that you cannot solve, you either solve a different problem, right? Or you simplify your assumption. You make the model basically solve. You look at a subset of that, or either you solve a different problem completely. That's what we do most of the time. We have a nonlinear system. We say no, it's linear. Then we can solve it, right? And that's anyway. Unstructured uncertainties is the other approach in here, where now you don't know the parameters, you don't know the order. You just know I collected data, and it feels or it looks like it's going to be in this regime. Now, this is where things like neural networks appear, but in the linear case, what you do is you can put a band of uncertainty in the frequency domain around both the magnitude and the phase of your transfer function. This turns out to be theoretically appealing, but in general, it results in high order. And believe it or not, this was the so-called robust control approach. It turns out robust controllers that are fragile. What does that mean? So they're very robust because they can handle a lot of uncertainties. But they're very fragile because unless you implement them exactly, they screw up everything. In fact, one of my favorite examples of this is there was this open problem that these people solved, and I was a reviewer of the paper, And I recommended, I looked at the example that they gave, and I recommended that, maybe, you're carrying your calculations, 8 significant digits or whatever it is, that doesn't make, it shouldn't be. It's an engineering journal, maybe you should try to do something else. And, the paper appeared. They thanked the reviewers, the careful reviewers, and so on and so forth. Appeared, and about 2 or 3 years later, I had a student, and I said, why don't you try to implement this? So he goes to implement the example. And it was, when I say implement, by the way, simulation at that time, not really to do it. So he goes in, he tries, and he said, it doesn't work. I'm like, no, these people are careful. I reviewed the paper. It's good paper, blah, blah, blah. Go and do it. Tries again. It doesn't work. So he comes to me, and then I try it. It doesn't work. And we're using, MATLAB simulation and so on. So I contact the authors, and I said, look, I want to tell you, I was one of the reviewers. You didn't know this. Oh, yeah. And I said, well, could you tell me about this example? He said, well, I didn't do it. My colleague did it, my co-author. Okay. I called the co-author. Co-author tells me, oh, well, my student did it, and he sent me the files and so on. It's exactly what we're doing. It doesn't work. We dig and dig and dig until we figure out it was the way we were using Sun, Spark, I don't know which model back then, and some operating system. We were using a different version of the operating system, inputting exactly the same thing. It wasn't working because of this problem. These things were so fragile, they had to, even if I carried out the, so this is, engineering-wise, this is a useless design. You can't have something, that where you have to implement exactly 8 significant digits, and if you have 2 different implementations, things don't work. So anyway, so this is a really terrible thing that when, I was talking to you yesterday about it, is sometimes you want to back away from optimality, because at that edge between, when you get something to be optimal, you're probably sacrificing something else if you're not accounting for, and it may go bad on you. Anyway, this is an interesting thing here. For a while, people said, okay, look, nice and good, but I don't want to spend too much time modeling. What I want to do is I want to take a controller and I want to put it on a second-order system, and it should work, this controller. So it came to be known as universal controller. It turns out you can actually show that all you need to control a system is one piece of information, which is to know that this system can be controlled. That's it. If you know the system can be controlled, there will exist a controller mathematically that will do the job, and there is a way to find it. The problem is, I say they do not exist. They do not exist in the sense that if you try to do that, what this controller tries to do is basically shake the system all the way and break it before it gets to find the actual control that it needs. So in a way, it's not surprising. What you're doing is you give me a black box. All I know is that it's a linear time-invariant system. I don't know the order. All I know is it can be controlled. Then there is a way to basically implement an algorithm mathematically that basically is you can prove that this controller will work for any of these systems. It's the holy grail. And this is the too good to be true result that I told you. It doesn't really exist, because what happens, even in simulation, it will swamp the computer, whatever computer you have. I don't know what your latest system is, but it will swamp it will go 10 to the 50 or whatever it is inputs and so on before it settles down. So it doesn't really work. That's one of the issues that I think. What do I have? Should I stop? Should I do? I'm probably over. Okay. So one of the things that's happening these days is this. I mentioned to you network control systems, and remember before I put a plant, I put a wire from the plant, everything was localized, everything was dedicated, and so on. Well, what's happening more and more is the plant is somewhere, and you're controlling across a network that's shared by other things. Or you have this obviously it's for a special customer here, but you have this cloud of controllers, let's say, or they're satellites supposedly, and they're trying to talk to this network of different systems in here. Now there's a low control level here where each one of these is doing its own thing, but they're also getting information from somewhere else in here. Now what starts happening here is that you solve one problem, you introduce a bunch of others, and mainly the problems have to do there with delays and with the fact that you now have to worry about who gets access to this to this network. How do I make this, let's say these applications here, they're just, chatting here, twittering, or whatever they're doing. This plant here is a nuclear power plant that's about to blow. Of course, I wouldn't put it on the same thing, but let's say we have more important things. You're in a car. The car right now, your car is controlled, you have a network that's controlling a lot of things. Okay, it's controlling the AC, but it's also monitoring your speed. It's also doing some other things. Well, which one gets priorities? Okay, you have delays. You have issues of access control. Oops. Okay, I'm not supposed to do that, so now, okay. So the interesting thing, the reason this is in here is because this is yet another one of those things that really cuts across to take you from one domain to the other. And this is a link actually between control theory and information theory. Okay? This is a result that says if you have a channel that you're communicating across, normally all you need is observability and stabilizability to be able to control a system. What does that mean? That translates in the linear time invariant case, the fact that you don't have pole zero cancellation. There is no common pole zero cancellation. So if you have that, you can design a controller if you have a dedicated channel. But now you're going across this noiseless channel, and it turns out that the capacity of the channel needs to be larger than, the rate that you have to communicate across is going to have to be larger than the sum of the unstable eigenvalues of the system. What does that mean? Well, normally, I don't care about this. I don't care about this because I'm communicating at infinite precision and infinite speed. But in reality, even though you design a controller that can work, once you start communicating across a channel and you're sending information that's going to be packetized, and we're not even talking about that yet. We're just saying that even if you can send everything exactly, you have to have a rate higher than how unstable the system is. Let me give you an example to give you a feeling of this. You're driving your car, and you stayed up late working on whatever the latest project you guys are working on in here that has to go out in a couple of days. So you're working late, and then you get up the next morning, you're tired, go out of your driveway, and you doze off a little bit. You wake up, you're okay if you're in the driveway, basically because you're not going too fast. The system dynamics are not too fast. It's unstable, but it's not too fast. So the rate that you have to pay attention to in order to apply the control is slow, small. You can do it. You're driving on the highway, you do that, you're gone, right? Because the system is highly unstable. You have to pay more attention. In fact, you have to pay constant attention, or you cannot be texting. Cannot be texting if you're doing this, right? Okay. So that's kind of what this is making formal, but the nice thing about it is this is one of those fundamental laws. This is one of those things that basically tells you, everything we were doing up to that point, we were assuming that this channel is infinite capacity. Well, it's not, but for all practical purposes, we have a dedicated channel and so on, but it was good. Now that we're having to control things or send messages across the network, that's not what should happen. The final thing I want to one of the final things, I guess, is the resource allocation as a control problem. Now, this is really one of the best applications, I think, and it's related to what you've been doing. There's a book, it's not, the original work is not by Shrikant, but this book is probably the place where it puts things together. And so really what you have here is you have a network, you have a source you have an origin and destination. We call that a source. And what you're trying to do is control the rate, the transmission rate. So I'm going to put a few definitions, for a couple of slides in here. So XR is the data transmission rate in bits per second, and each link has a certain capacity. Now, what you want to do, and this is what Kelly did, is he defined the congestion control algorithm. He defined them as the idea of maximizing the utility, the sum of all the source utilities. And it turns out, if you make some assumptions on this, you get different, let's go in here. You make some assumptions on these, you get mathematically nice results. It's not exactly what's happening, but this explains it. So, and these are some classes of utility functions that give you like the minimum potential delay, or the proportional fairness, or so on and so forth. So basically, by defining these things, you end up with different congestion control algorithm. Now, here's the problem with this. All of this up to that point assumes that you have this supervisor, this hypervisor, whatever, controlling everything. That's not what happens when you put a node on the network. Nobody knows about everything. So what do you need? You need feedback. And this is what happens. Really what happens here, these are sources and these are links in here. And you want to design the dynamics in here so that the sources are not supposed to know about everything about everyone else. Each one of the sources is going to know, for example, that my message got there or it didn't get there. That's all it needs to know. The links do not care about the particular sources or about what other links are doing. All they need to know is that, I'm getting more traffic than my capacity or what I can handle. So they're getting feedback, but it's going to be implemented, the control is going to be implemented in a distributed way. And let me get to the end here, to the punchline. The punchline is, okay, this is, oops, what is the equation? Oh, it's supposed to be in a couple of equations here. That's your, okay. So basically, there is a primal dual algorithm here that's doing an optimization, it's one algorithm that's doing two optimizations that are maximizing the utility of everybody in a distributed fashion, where each one of the nodes, the sources or the links, are getting just enough information to solve that problem in a distributed way. And then, this is why I wanted to put this in here, because now you get to a situation where you no longer can just discuss it from the simple linear time invariant case. Once you get to a complicated thing like this, you probably want to talk about it in a state space format where you talk about global or about stability in a different sense using Lyapunov or so on and so forth. And this is what this approach basically does, is explain why congestion control works on the internet from a system theoretic, more control theory, more optimization point of view. And that's really one of the keys, I think, is to try to explain or to try to do distributed resource allocation. Okay, the final one here is actually the work, a couple of the slides from, we had a student here in the summer who worked with one of your groups to look at designing controllers for some of your data centers and so on. This is really, you remember the steps I talked to you about? I said, okay, you take the system, which is right here someplace. You decide what the control inputs are. You try to fit a model. What is the control input? What are the outputs? You try to fit a model to this system. You identify, you use least square and so on to identify the parameters of your model. You end up with something like this. So this is what it's a multi-input, multi-output system versus single input, single output. But that's really what they did. They came up with signals that they can measure and use to feedback. There are some things that are disturbances they cannot adjust, and there is also noise. And then once they have this model, they actually designed the controller in here. And then my understanding is they tested it on a small scale system, and it worked beautifully. Or, well, I don't know how well. I don't know if it's, full scale and so on. But basically, once you have the system, in this configuration here, he's using the model to design the controller, but then applying it to the actual system in here. And there is a variety of things to do, for example, to adjust the model online if things are not happening. So this was an application, a straightforward application of some of the basic concepts of modeling and control to some of the problems in here.
The previous one looks like an observer, but the observer is missing.
Okay, which one? This one or this one?
No, that one.
This one? Okay, so this is like a model following control. But you're right. I mean, if you were to be able to estimate the state, that would be an observer. But see, yeah, exactly. What happened in this case, it turns out this system didn't have any dynamics. It was a static system, so they didn't really need that. But you're right. I mean, you could be, you're thinking the right ways to get the observer to construct the state and feed that. So let me talk about some of the other control issues that you may run into, or you may some of the tools maybe also. Most systems are nonlinear. So there's a whole, all I mentioned about nonlinear is that I just mentioned things about global asymptotic stability. But nonlinear systems, for a while, all we would do is linearize and say, okay, we're going to apply linear techniques and stay in the linear regime. Since the 80s, 90s, and so on, and since discovering what people did in the 1900s, we understand a lot more about nonlinear systems. So we don't need to linearize to hit everything with linear techniques. Although linear controllers work, or controllers on many of these systems. So, this is really, if I had to get something out, is that most systems are uncertain by design, or because they're either too complicated, or you don't want to model them exactly as accurately as you can, because it may not pay. So if you model the uncertainty, you may be able to do a lot of things. So first principle modeling is very difficult in computing, very difficult. In fact, I'm not aware of any work that says, okay, you put this in, this is what you will get out for, in something like Newton's law of something. There's nothing like that. So you're not going to get, you have to use data-driven techniques to do the modeling. The control objectives that you probably have are more tracking and optimization in general, rather than, regulation is a simple thing, but tracking, you may be tracking, the power, the data centers you may want to track or optimize, your power consumption subject to being able to serve so many, and so on and so forth. I didn't talk about the state space approaches, and one of them that was very successful is the so-called linear quadratic regulator or linear quadratic Gaussian controllers. These are very nice if you have the good state space model. This is actually what gave rise to these robust control techniques, because if you don't have a good state space model, or if you only have access to the output and there's noise in it, it turns out that the so-called optimal design is actually really bad, that creates problems for you. The advanced nonlinear techniques I mentioned here, that you have nonlinear systems, but there's about 5 different layers from that where you can get better techniques that kind of use your knowledge of the system. And then finally, there's a lot of interest these days about game theoretic approaches, especially in distributed systems. So what you can do in that case is to say, okay, these different nodes, sensor nodes and so on, are playing a game. They're part of a game. You can call on a lot of nice results and nice approaches to do some control designs. Yeah, sure.
So when you refer to the optimal, are you referring to the optimal control theory where you use power variation, so on?
Right. So that's an excellent question, because when you say optimal, you have to say with respect to X, with respect to something. So when I say optimal in here, what I was talking about is what, for a while, and this is the 70s and 80s, when people were enamored with the fact that you can design controllers that will, optimal control, basically. And then there's a really nice paper that says good, optimal, or bad, basically, which showed that, you cannot really have, something that's optimal with respect to something could be bad if you violate one small assumption. And that's, I think, one of those practical things, the too good to be true type things, is that, when someone says optimal, they're designing for, optimal with respect to this performance objective subject to these assumptions. And then when you try to put it together, it turns out to be, in this case, for example, it turns out there's a kludge to fix the original problem, but then it turns out to open up a lot of other things. So that's exactly what I'm referring to. But there's optimal control for nonlinear systems. There's optimal control for a lot of things. Very, very interesting and rich area by itself. So these are some of the tools, some of the new tools also in the new applications. So this is what we started discussing because of the cloud computing and data centers. And here what you have to do is, you have a distributed control problem. There is no centralized, or hopefully, eventually you don't want to centralize. You start out by designing something where the control commands or the sensing goes through a central node, central operator that can make decisions. Eventually, that's not really such a good idea, both for reasons of having a single point of failure, but also for reasons that the network latency and so on may cause problems that I mentioned before. There's the economics of it, and I mean by these the game theoretic stuff and some of the other issues that are really getting into the field of control. This modeling of the uncertainties. This is interesting. A hybrid system is a system, actually, this is very interesting because what you have is, I mentioned before, you either have a continuous time system or a discrete time system. Well, what you're assuming is once this model is there, it's there, even if it's time varying. What happens in some cases, and the simplest example would be a car where you're shifting. What happens is you have different models in different regimes. That may be one way to deal with nonlinear systems, is to say, okay, in this system I have a linear, in this regime I have a linear model. So I'm in first gear, and this is the equations. These are the equations describing my car. I switch to second gear, I'm in a different regime. So these systems are called hybrid because they have dynamics that are, I would say, continuous dynamics, not continuous time, but continuous dynamics. They're proceeding according to differential or difference equations, but then an event happens and they switch into a different one. So you have both a discrete event system that's controlling the dynamics of the system. And that's really what computing systems are, really. A lot of times you have something, it's proceeding according to some, precondition, pre-design application, and then an event happens, either something external or because the state of the system reaches a region where you have to shut down something. That's a different, so either internally to the system, you have an event that happens, or something happens from the outside. Somebody tripped over a power cord and took out half of the system or so on. This one is always interesting. It's this idea of distributed control of network systems. You have a lot of systems that can do their own thing, but then how do they come together in a cohesive way? That's what happens to the internet. That's what that congestion control algorithm is really doing. It's doing things so that collectively you're optimizing something that benefits everyone, but at each one is doing something else. So I want to leave you with a couple of slides on some parting thoughts, and then hopefully answer some questions. So I love these quotes because you hear something and say, yeah, that verifies exactly what I mean. And then you see somebody else to say, delay. So don't delay because the best is the enemy of the good. But then Gordon Moore says, okay, delay, delay, delay. In fact, the best quotes are the ones that the same person says two opposite things, right? I don't have one of them in here. But basically, this is actually one of my favorites because in some cases I did some work in time delay systems where it's actually best to delay acting, wait before you act. And it turns out there are some systems you have a delay already built in the system, such as you're controlling something over a distance. If you try to act right away, you actually cause instability or you cannot control it. But if you wait, then you actually can stabilize something. And it's counterintuitive, but it turns out to be, mathematically provable, and in practice it works. This is mine. So, control without power is useless. Power without control is dangerous. It should say, not useless. So, anyway, this is the end of the talk. But every time I give a talk to some new audience, I wanna present this question because it really bothers me a lot that in a lot of my problems, I can solve everything for two systems or two nodes or two something. I go to three and all hell breaks loose. I have no idea why that is. So if you have examples of that, let me have them. But if you don't, if you want to think about it, this is the two in here are in control. We can simultaneously stabilize two systems. I can take two systems and I can tell you whether I can design one controller that will stabilize both of these at the same time. One controller, it doesn't change, it's not an adaptive controller. So if you have two operating points, two operating conditions, I can design one controller. I'm talking linear time invariant simple system. Three systems, no idea. No idea. I mean, it's actually provably undecidable. It's translatable to the other one. This other one here, adaptive control, where you try to adapt to the system. If you do adaptive control for two systems, it's easy. When you go to three, all hell breaks loose. It turns out to be okay, actually. You can solve it, but it's really so much more complicated. So I don't know. This is just has nothing to do with the talk. I just want to see. Well, I figured I'm going to talk to some smart people, so if you want to think about them, let me know. This is interesting, the drunken walk in 2D lattice. I told this to one of my advisors, And I said, do you know what I'm talking about? I said, I know exactly what you're talking about. And he started rattling, and he said, this is one of his problems, is in a 2D lattice, if you go random walk, you have a, 100% probability you're going to reach every point, including the starting point here. That doesn't happen in 3D. So if you know something about it, let me know. Point me to some place. If you don't.
I guess in graph theory.
Okay, tell me about, yeah. So what happens in graph theory?
When you want to solve problem matching for
Yeah.
like you want to choose a husband and wife.
Yeah, yeah.
It's normally time doable.
Yeah.
But if it's 3, then it's NP.
That's right. So that's one of the examples. I didn't put all the examples, but I thought you were going to explain it from graph theory, because one person started telling me, he said, well, look, if you have 2 nodes, there's only one relationship, one thing you can do between them. As soon as you have 3, you have multiple relations. So, well, yeah, that's okay. That doesn't solve anything. It just tells me that somebody else told me, relationship between 2 people is easier than relationship between 3. But, that doesn't solve anything. That just makes it. Anyway, so that's all I have. I'm open to questions. Thank you for your attention. Yeah.
So you talked about universal control, and you mentioned systems are either controllable. There is one bit of information that the system is either controllable or not. So how do you find a system is controllable or not?
Right. So for linear time invariant systems, which are the first level of modeling or approximating a system. If you're looking at it as a transfer function, all you need to do is look at the numerator and the denominator. If there's no pole zero cancellation, if there's no, let's say the numerator is z plus 5 over, and the denominator z minus 2 times z plus 1. There's nothing that's the same. You can solve the problem. And in the state space domain, you can say that you can find a minimal realization, which is controllable and observable, or more accurately, really the problem is you can cancel things as long as they're not unstable. You can cancel them, and that becomes a little bit less. But basically, there's a test. There's a test that's mathematically rigid and so on. And it turns out this is, one of those too good to be true but practically useful, is that genetically any system you can come up with is controllable and observable. You can do it genetically for any linear time invariant system. Basically because it's very hard to have things exactly the same. Now practically that's not the case, because the reason you have this pole zero cancellation is exactly because when you're modeling your system, there are terms that appear in both places. So practically that's not useful, but genetically, in the mathematical sense, it's very hard to line things up on top of each other exactly. So it turns out everything is controllable, observable in general, but practically that's not. No, see, black box, that's what, yeah. If you have a black box, you don't know no. I mean, so this is what, see, so black box, the first thing you want to do is really model. And model in the sense that I'm talking about. Put some inputs in. Don't put a white noise and so on. Start with things that are supposed to be available. Collect the output. Start with that. Now, if your system is unstable, and it could be, if it's nonlinear, it could be unstable to some inputs but not to others, you're in trouble. So in that case, there's some closed loop identifications where you can put some kind of a controller on it to try to guarantee stability. But really with the black box, you start, someone told me once, there is no black box, it's a gray box. It's always a gray box. You know something. I mean, if I do this, so you want to start with something, a little bit of your knowledge, and every bit of knowledge helps. Everything, you have, So this is the other thing that I object to in many cases where people say, okay, look, I put a neural networks on it and look how it works. Well, really, you threw away a lot of knowledge by putting the neural networks. If you don't know the system at all, I wouldn't start by putting a neural network. I don't know what it's going to do. And if you do know something, use it. Don't use, something that's just I put something in here, for a while there, you could buy these routines, these canned routines, and say, okay, control your, pendulum or whatever it is, and so on. The other thing you'll notice is when this thing was, when these so-called intelligent control approaches came about, they were always used in things like a washing machine and things like that, which are so what if it doesn't work 100%? I mean, who's going to be able to tell? You can hold two pieces of white next to each other or something. You wouldn't hold it, you wouldn't use it in an airplane. You wouldn't use it in things that have real consequences in a computer system. You would not do that without, I'm not saying they won't work, but without doing all of these other tests and verifications and so on. You wouldn't do it. You wouldn't ship a software just because it worked once. What? Of course not. Yes.
I think I'm kind of familiar with some of the work you mentioned, the application of control in like quality of service.
Right.
And optimizing some parameters.
Right.
Provide some
Right.
service requirement.
Right.
Now, the problem with that is, let's say I had an experience with a three-tier machine. With a three-tier machine where you have like...
I'm sorry, what kind of machine?
Three-tier machine, the web application.
Right.
And the problem is that we have 20, 30 different parameters.
Right.
And your performance measure would be the throughput. Now the question is, how do you model the throughput as a function of so many different parameters?
So that's an excellent question. So back to the modeling. So you're familiar with some of these, and from the discussion with Ripal, he tells me, oh well, they started doing this, but then these people stopped doing it, or it didn't pan out or something. So here's what I think. I don't know the exact answer. How do you model one parameter with respect to that? But I can tell you based on other experiences what you would do. The first step of any of these is to really connect the control theorist with the domain expert, not have the control theorist try to do this. Because if I came across some of that problem, one of your problems, I'll just make a bunch of assumptions that don't make any sense in practice and say, look, I solved the problem. Okay? And if you try to do it from the controls point of view, you'll say, okay, look, I found out PID. Everybody says PID. I put it in. It worked on this, but it didn't work on that. And that's what's been happening. That's why I think it's interesting. Some of the people who are recently involved with this is that, there's some control theorists that are trying to learn the language of the other one and so on. So having said that, I know when I started working, for example, in the load balancing problem, again, same issue. We couldn't agree with the computer engineers. What is it exactly that the parameters that you wanted to control, or they would say, oh, I have this parameter. I say, no, that's not a parameter. That's a signal. I needed to make sure that we understand each other's language. When we got to the point where we finally convinced each other that we have I don't want to say a predictive model, but an approximate model that gets in, then feedback. And we use that in order to design our controller. Then the action of feedback, again, helps a lot if your model is really captures some of these parameters. So if you say, okay, I want to maximize the throughput in here, but I have all of these other things in here, how do I make sure that the effect of one of them is present in there, and how they interact with each other? Well, I would start by saying, okay, keep everything else constant. Change one of them, see what happens to the throughput. That gives me one transfer function. So it's a multiple input, one output. That's how I would start. And it may not be a transfer function, but a relationship. It's not necessarily a linear time invariant type relation. Then I would do another one. Then I would do another one. Then I would do another one. Now that doesn't work. The reason it doesn't work is because there's an interplay between some of them also. So what I'm doing is I'm learning kind of like the diagonal thing, if you will. But there's some things that are across. So then you have to go to a second level, maybe, and try to move two of them, and so on and so forth. Now, ultimately, this becomes very expensive and maybe not the right way to do it. So you go back and you say, okay, I know that this is my most important parameter or most important thing. I'm going to schedule based on this, and then whatever I have for control effort after that, then I will use it to adjust something else. So, again, it's not really like an answer to say, I have a model for you. I don't. And in fact, from all of our discussions, when people tell me I have a control problem, usually they have a modeling problem. Because once you have the model that explains it, the controller is almost like staring you in the face. It's telling you, okay, take this, multiply by this, or look it up in here. So the modeling is really where this thing is at,
Definitely agree with you, and I think that's what they do. They come up with some statistical methods to figure out what are the important factors. But
sure.
One other thing that happens here is sometimes the data that you collect is so expensive.
Right.
Like if you want to collect the throughput with respect to one parameter, it takes you half an hour.
Sure.
So you run the experiment and everything does down. So now you have very few number of
Yes, and Microsoft. Are you correct? Were you worried about these things? Yeah.
So
Yeah.
I think
Yeah.
Keep in mind that, well, normally for these things to work, we need a lot of
Sure.
data.
Sure.
Like maybe 50, 60 different data sets.
Sure. So that's another great question, and it relates to some work I do also with people in the medical or bio kind of data, where again it's very expensive and it's very rare that you get a lot of data. But then you get into the things that give you confidence in your model, because as you know, if you want to learn something, depending on the complexity of that what you're trying to learn, you can measure how much data, or you can bound how much data you want to do, and so on. So if you don't have that, then now you got to model the uncertainty. You can say, okay, look, I'm confident with this with 50%. I'm not and then update it. But to me, you're going to have to spend the time doing it, or putting, you're going to expense it either at the beginning or throughout. And eventually, if the benefits, I mean, why do people not use the nicest possible control or whatever? It's because the benefit compared to the cost is not there. So if you want the benefit, and that's why the aerospace industry would, or because they have lives at stake. So the question becomes, how much are you going to save if you have, if you have a controller that will adjust? How much are you going to save? What, are you going to make 1,000 more customers happy, or you're going to save so much money that people will pay for this to be designed and deployed? Otherwise, when energy was cheap, who cared about how much it took to cool the data center, or to, we didn't care about it. We only care about it when we try now to squeeze more performance. And I think that's what I'm saying, is that you either spend the energy in calories and brain calories, or you spend it, in money. So decide how you want to do it, I guess. Thank you.